Okay, back to the discharging. Discharging, this is an example about charging, but let's first quickly go through the discharging process. In the discharging process, you can expect that let me talk, even though the book is starting from the voltage, but when I say discharge, I'm talking about charge. So for me, for my brain, it is better to talk about charge before the voltage. Discharging, it means we are starting from maximum charge ending into almost zero. Maximum charge means maximum voltage, because we have agreed on that already, that the charge is directly proportional to the voltage across the capacitor. Q is equal CV. So we started from maximum, which either you will say V naught, which is the maximum voltage across the capacitor, which is actually the epsilon, which is the charge of the battery. But why did he say V naught this time, but he didn't even draw the battery? Let me tell you something, and you have to be very careful with that. After we do the discharging, after we do the charging where the switch was closed, and we do the charging, and then, when the discharging happened, where we, of course, open the switch and then close it again, because either charging, you have to know that, or discharging, both of them, the switch should be closed. Why? Because if it's open, nothing will happen. The circuit itself will be open, so nothing will happen. So when they say the capacitor is charged and now we close the switch, it means the current will be running again. But this time, what will be the source of the current? Or what will be the motivation or the electromotive force behind moving of the current? It is the capacitor itself. It's not the battery this time. All right? So this is very big difference between charging and discharging. In the charging process, the source of the current moving inside the circuit is the battery. In the discharging, we already have charge on the capacitor. And since we have charge, Q is equal to CV, so we have voltage, and it reaches anywhere to maximum. All right? So the source of that moving current will be the capacitor itself. So we start from the voltage, the maximum voltage across the capacitor, which is basically the electromotive, source, the power supply. It's the same value. But the source of the current here, the source of the current in the discharging, the source of the current is the capacitor itself. All right. So what do you expect the graph, the equation of the graph? It looks like the current one. So it is V across the capacitor is equal maximum voltage across the capacitor, which is in value is the epsilon, times only this exponential minus t over tau, or RC. The nice thing in all equations, this doesn't change. It's always exponential minus t over tau. It doesn't change. All right? And the same thing, the charge will have exactly the same equation, except the V and the Q. All right? What about the current? Luckily, the current will have the same graph as the charging. Why? Because even though the source of the current is different, but we will start with maximum current again, we end up in zero when the fully discharged capacitor, when the capacitor is fully discharged. So in discharging current, voltage across the capacitor, charge of the capacitor, they all have the same looking graph. All right, now we can move into some kind of examples. All right, in the examples, always you need to pay attention. Does he talk about charging or discharging? Because it makes a big difference. You have the equations with you, but in the formula sheet, they will not tell you whether this is a formula for charging or discharging. You have to know it. And here he's explaining to you the exponential, that E is not the electron. E is literally the Euler number, which is 2.718 if you don't know. But anyway, in the calculator, there is the E thing. okay, where the natural logarithm of the e is 1. This is a very important, this form, this and this, they are very important when we will solve some problems. That when we have the natural logarithm of the exponential is equal to 1, and the natural logarithm of the exponential to the power of anything, it is that thing, the power. Okay, let's see this example and let's see what's going on. Let's imagine that we don't know whether we are in the charging or the discharging. The capacitance in the circuit of the same circuit, the RC circuit. So C is given in microfarad, and be careful, micro, kilo, you should know these prefixes. This will not be given to you, okay, unless it's very, like, you know, all of them, like this is 10 to the power minus 6, this is 10 to the power 3. Okay, so C is given, R is given, and it says the battery, so electromotive force is given. Okay, now it says determine the time constant. Easy. Tau is R times C, but be careful, the R should be in ohm, so it's 20 times 10 to the power 3 ohm. Okay, C is, it should be in Faraday, so it is 0.3 times 10 to the power minus 6 Faraday. Okay, so be careful, you should do the conversion, and then whatever the number, directly you can write in seconds. You don't have to go through proving that it's in seconds. It's known that it's in seconds. All right, so this is the time constant, you calculate it. Now it says find the maximum charge the capacitor could acquire. Okay, the maximum charge. Okay, so we are in the charging process. Let me just quickly sketch the RC circuit. Regardless how you will sketch it, it doesn't really matter, because finally you should know that there is R and there is C, okay, and there is epsilon. All right, so he's saying find the maximum charge. Maximum charge, like I mentioned in the previous videos, that the maximum charge happen when full charge is done, so there is no current flowing, so there is no voltage drop. V is equal IR is not there across the resistor, so Q is equal CV, so the maximum charge Q is equal the capacitor value times the maximum voltage. What is the maximum voltage that the capacitor can have? Is the power source. All right, so what is the maximum charge? It is our C, which is given, times the electromotive force. All right, and this is in this is charge, so it will be in coulomb. Okay, clear here? I hope. Now so you got it, the maximum, so there is no current, so there is no voltage drop across the R, so we just have the simple equation. Now it says the time it takes for the charge. This is tricky, and I really solved the question because of this part. It says the time it takes for the charge to reach 99% of this value. So this is Q maximum, which is, let me just see here, Q maximum is 3.6 microcoulomb, all right? And he said, I want the time. Where the time comes from? In which equation? In the charging equation. And he's talking about charge. So it is Q across the capacitor is equal Q maximum, or Q naught, whatever you want to call it, 1 minus E minus T over tau, or RC, is, that's it. This is the equation. So when he said the time, it means he's asking for T, all right, that it takes for the charge to reach 99% of that value. So this is a Q maximum that we have calculated in part B. He wants the time that it takes for the charge to reach only 99% of Q maximum. Again, this is the tricky part. Okay, it says he wants the time it takes for the charge, so Q across the capacitor will reach to 99%. Whenever we are dealing with numbers, we do them like that, of that value of Q maximum. So Q across the capacitor should reach to 99% of the Q maximum. Actually, to tell you the truth, you don't really need to know what is the value of a Q maximum to solve this problem. You know why? Let's do the math. Minus T I want. Tau, you need it, because finally you have to plug in tau, but I will just keep it tau for now, for less confusion. Imagine for any reason you calculated tau wrong. So why to mess up your equation? Just try tau. Whether you calculate Q maximum or not, this is multiplication, right? So can we divide both sides by Q maximum? So this Q maximum will cancel out basically because we divide both equation sides by Q maximum. So we say 0.99 is equal 1 minus e to the power minus t over tau. Tau is known. I will try to solve for t. All right. So we can separate the exponential part. How do we do that? We can bring this to the other side. So it is e minus t over tau, and we can bring this one to the other side because I want to isolate the exponential. 1 minus, because when it comes to the other side, 0.99. All right, which is, what is the value here? 0.01, right? Now, how to get rid of the exponential term? We take the logarithm, the natural logarithm of this is equal the natural logarithm of 0.01. Keep going. We just mentioned that we cancel this and we end up with minus t over tau is equal len 0.01. Continue. So we are there. T is equal minus tau, natural logarithm of 0.01. Tau we already calculated in part A, and this is in seconds. This is the time, which is very small time if you see. Okay, it's very small time. It's 28 milliseconds basically. It's very short time. You see? So it means that you can, within very short time, you can reach almost to the full charge in this kind of circuit. Great. Now, I hope that you can go through this math again, because this is very important math to do. All right, and you can go through it again. That's why I am recording YouTube, so you can go through it again. And again, we are using this property of the natural logarithm. All right, part D, what is the maximum current? Okay, now maximum current we already mentioned. When do we reach to the maximum current? In charging a process, it means we don't have charge over the capacitor, so there is no voltage drop across the capacitor. So the maximum current will be just simply V is equal IR. So I is equal the maximum voltage divided by the resistor. What is the maximum voltage? Is the voltage of the battery, and this is what you can see here. It is the voltage of the battery, the voltage of the battery divided by R, and this is the maximum current, which we get once we close the switch. All right, the moment when the switch is closed. So this is a very good example about charging process. It hits each and everything, and this is really important for your final exam. I will end here, and I will come to another YouTube with a discharging example.